Hello, everyone. This is my great pleasure to give this invited talk as a part of the Pre-Early Career Award in the IAFSS International Symposium. So as part of the award, I'm invited to give a review on a selected topic. So here, I choose the topic is the near limit opposed file spread. Of course, this is a very broad topic, so very difficult to review within 20 minutes. So I will just try to focus on these interesting fire phenomena and rather than the detailed series. So if anyone who is interested in more detailed, please look at this paper. It's already available online in the Fire Safety Journal. So in terms of the fire spread, this is a relatively old topic. So about 70 years ago, one of our founding father, Professor Howard Emmons, has already written in an excellent review in his article on fire in the forest. In that review, he already explicitly explained the process of fire spread is fundamentally a continuous ignition process. That's the reason in modern days, many of these, we have many of the fire spread testing facility are actually doing the ignition test, but they are fundamentally the same because if we know how the fuel are ignited, we can quantify the fire spread behavior on that kind of fuel. And later on, my supervisor, Professor Foreman Williams, wrote another review in 1977 is a mechanism of the fire spread, which is, I think, one of the best review in this topic. And he essentially write down all the equations we need to explain most of these fire spread behaviors. Then later on, Professor Fernandez-Peyo and Professor Hirano write another excellent review on the controlling mechanism of flame spread. So basically trying to quantify the contribution of heat transfer from gas phase and the solid phase, which both are important in terms of the fire spread. And of course, there are many other excellent researchers have made significant contribution into this area. For example, Dr. DeRis, Dr. Kashiwagi, and Dr. Ross on the flame spread process, and also Dr. Rossmer and Franson for the wildland fire spread, and Dr. Ola Miller for the smothering spread. So essentially, we are all standing on the shoulders of giants. So we have understand a lot about the fire spread over the last half century. So the reason of doing this review, basically I have two motivations. The first is 3 years ago, Professor Michael Goldner, who is the guy actually introduced me to the fire research at the first place. He won the last Proulx Early Career Award, and he did a review on concurrent fire spread. So I think it's good to do another compulsory review on compensatory review on opposed fire spread, so we can review the entire topic better. Another thing is Professor Wickman had another excellent review on opposed flame spread 20 years ago, and that review is very fundamental and very theoretical. But there has already been many new development in this area over the last 20 years, and also that review does not cover the smothering part. So I think it's good time for us to do a new review talking about the new development in the opposed fire spread. So near limit review, near what kind of limit? So I will basically cover 4 different limits for this fire spread behavior, including the extinction limit. As we know, sometimes the extinction of a kind of fire is also ignition of a new fire. So basically the limit between extinction and ignition, many of the transition behaviors are related to this limit. The other is the limit between opposed and concurrent fire spread. It's very, sometimes when the oxygen supply is very limited, the boundary between opposed and concurrent fire spread is really not easy to tell. There are some special behaviors such as the fingering behaviors, and also the limits between the flaming and the smothering. There are some transition in between and also coexistence fire behavior. and also the oxygen limited and the fuel limited fire spread behavior. That will be the focus of the review. But I will briefly touch this topic in this presentation. So first, if we can look at the oxygen supply, so if we reducing the oxygen supply, we will see the fire become very differently. So initially we have a lot of oxygen supply and the flame is basically yellow. And now if we put the flame into a narrow channel, and you can see the flame become blue, and there are some special fire behaviors like a fingering. And if you put a flame into a porous media, then the flame are very difficult to survive. It's almost pushing the limit. And further reducing the size of the pool, essentially fire will be quenched. So only smothering process can be involved. So I think it's good to review these special behavior under the limited or excessive oxygen supply. So how do we reduce oxygen supply? There are typically three ways. First, you can remove the buoyancy, such as doing experiment in the microgravity or put that in a narrow channel or porous medium. And also you can reduce oxygen supply, flow velocity. Putting in the porous media is a good way, and narrow channel will also do that. And the last thing, you can reduce oxygen concentration. Then the flame or the fire will not sustain. So introducing the concept of limiting oxygen concentration. So let's look at it first. Is the influence of buoyancy. So if we can reduce the buoyancy, we can create oxygen limited environment. So one of the key parameters here is the Grashof number, basically quantify the ratio between the buoyancy momentum and the diffusion momentum. If you look at this correlation, you can see if we can reduce the gravity, we can reduce the buoyancy effect significantly. Equally, we can do that by reducing the pressure value. If we can reduce the pressure, we can also simulate a low buoyancy process. What I want to emphasize here is the diffusion momentum is not sensitive to the pressure. So what we are changing is the buoyancy momentum. So the numerator is reduced, not increasing the influence of the diffusion. And another interesting thing to look at is the flame spread in microgravity. So this is an experiment done by Sandra Olsen 20 years ago. So basically, she ignited a fire in the center of the paper. So in the space environment, once you ignite in the center, where the flame spread in opposite direction or concurrent direction. In fact, in the microgravity environment, the oxygen supply is very limited. So the fire will trying to reaching out for the oxygen. So it will tend to move in the opposite direction. This is very different from the on Earth. On Earth, usually the upward and the concurrent fire spread will be dominating over the opposite because you have a lot of oxygen supply by the buoyancy. But in the microgravity, it's very different. So there are some new phenomena in the microgravity environment. And also, it is very difficult to observe the oxygen limited region on Earth because the buoyancy flow can be generated by the flame. And the flame, that flow velocity is usually about 0.3 meter per second or even 0.5 meter per second. And that's already sufficient oxygen supply for most of the flame. So that's the reason it's very difficult to observe the oxygen limited region. But in the microgravity experiment, it's very easy to observe this oxygen limited environment. And in terms of the extinguishing under limited oxygen concentration, so there are typically three kinds of extinction: smothering, quenching, and blow off. But fundamentally, I want to say they are essentially the same. They are all creating slow chemical reactions that is not sufficient to overcome the heat loss. So in that case, like the smothering, you reduce oxygen concentration, so you reduce oxygen oxidation reactions, which means the original heat loss become more important. And also you can blow off the flame by putting a lot of oxygen. Sometimes, so this cold air will cool off the flame, eventually cause a blow off. So essentially they are all quenching, I can say. And when near these extinction limit, many other influence factors like radiation heat loss from the flame and the solid, or conduction heat loss to the solid will become also important. That's the reason many people also call these oxygen limited region is like radiation extinction region, because in that region, these radiation heat loss become very important. Another interesting phenomenon to look at is the fingering process. That it also happens in oxygen limited environment. What's the fingering? Fingering is basically the fire front will break into separate regions. So each separate fire front will propagate independently and generate a fingering shape. And that fingering shape is very special, only occur in the oxygen limited environment. So it has been observed in the microgravity as well as in the narrow channel. And people have seen that for both flaming and smoldering process, as well as in the oxidation of the metal particles, as well as in the promixed ultra-lean promixed hydrogen flame. So actually, it's not very sensitive to the combustion process, but very sensitive to the oxygen supply. And many people has trying to use different non-dimensional number to quantify the limiting conditions for the fingering process, such as Parkland number, diffusivity, effective diffusivity, and effective Lewis number. I'm not trying to comment which one is better, but essentially they all trying to prove the transition happens when the diffusion lengths in the gas phase are comparable to the solid phase. In that case, you will have that kind of instability to generate the fingering shape. And here I'm showing you another figure. This is the fingering in the smoldering peat fire. You can see that the fire is not consuming all the soil on the ground. Instead, they generate into different separate front, and also causing the fingering process, although the scale is much larger. So I think this process is also worth to look into in future work. And when we talk about oxygen limited fire spread, we have to talk about the smoldering, because by default, smoldering is the very oxygen saving fire spread process. But it's not necessarily always true, because if the smoldering is near the surface, you still have a very sufficient oxygen supply. Only when the reaction front is deep into the porous media, then the oxygen supply through the porous media become quite limited. So the difference between, the similarity between the flame spread and the smoldering spread are very similar, except for the oxygen limited region can be easily observed in the smoldering fire spread, because that region can maintain a relatively large air velocity compared to the flame spread, which in the low flow velocity is buoyancy controlled region. Okay. So oxygen supply play a very important role in smoldering spread. So it's naturally we can think about is if you go deeper into the fuel, the oxygen supply will become smaller and smaller. So the fire spread rate will become smaller. Eventually it may stop right there. So the question is there a maximum depth for smoldering? So here I'll give you an example. This is a test we do in the laboratory. We have about 15 centimeter peat samples, and now it's already ignited. So the fire is already ignited, but the fire is spreading below the surface. It's difficult to see now, because even it generates a lot of smoke, it will be absorbed by the soil on the ground. Then after 3-4 hours, 5 hours, you can see the fire will propagate out, and you can see the flame. You can see the smoldering front. So this is a fascinating process. We still don't know if there is a maximum depth. And sometimes if you go deeper, actually the fire could be stronger because of the chimney effect. Another question is there a minimum oxygen concentration for smoldering? We know that there is one for flaming, but the value for the smoldering is not really understood. So I think the value will be much lower than the critical value for the flaming. And it's also depending on the testing condition, the airflow velocity. that's the reason the value is not fixed from the literature. I think this is also something we can further explore in the future work. So after we talk about the limited oxygen supply, we also look at when the oxygen supply is sufficient or even too much. The first thing look at is the spread to regression transition. When we have a fire spread on the surface, so we can see there is a continuous ignition process here. So the flame trying to move down by igniting new fuels. However, if you increasing the air opposed airflow velocity, eventually the flame can only hide in the recirculation zone, just similar to a candle. So this is not a flame thread because it's not trying to ignite the fuel below it. Instead, it's just purely burning process, just like the candle flame. So you can see the flame on the candle is staying in the wick. It's not trying to spreading down, attached to the wax. So there is some limit here. So the transition from the flame spread to purely regression, so no ignition process. So this concept is not very new because it's also well studied in the rocket propellant community. But in the fire process, it's not very well understood. So what do I think what happens is that transition happens when the opposed velocity is similar or close to the promixed flame spread, promixed flame burning velocity. That's the reason the triple flame in the flame leading edge cannot further moving down against the opposed flow rather than stay in the recirculation zone. So this is the first transition I want to mention. For the smothering fire, the transition, another important transition is the smothering to flaming transition. This happens when the oxygen supply becomes excessive. And Santoso wrote a very good review a few years ago, summarized the process involved in this smothering to flame transition. But in general, there are two causes for this transition. So first is people think this is a high temperature char oxidation, and the temperature is so high that it can pilot a flame. The second theory is it's auto ignition process of the promixed gas. But essentially, I think these two are very similar because inside the porous media, when the solid surface temperature are very high, it can either pilot the flame directly or it can help the promixed gas reaching the auto ignition limit. So essentially, I think they are the same. But how to quantify this transition is still very challenging. We need some new approach to understand that. That's the reason I want to introduce another topic is glowing spread. The glowing is a typical process when you see a very hot solid. The solid temperature is so high, it starts to radiate visible lights, dark blue, dark red or yellow light. So the temperature is very high, usually above 700 degrees Celsius. And for many cases, it's really difficult for you to quantify whether this process is a smoldering dominated or a flaming dominated. So essentially, they coexist together. So I could say this glowing process is actually a steady state intermediate between the smoldering and the flaming process. So this is a steady state condition, very different from the unstable smoldering to flaming transition. I show you an example. This is an experiment done by Professor Yuji Nagamura on the active carbon. So you see the fire is spreading inside these carbon particles. They're very bright, but it's really difficult to tell whether this is a flame or this is a smoldering front. In fact, so my co-author, Dr. Gao, has done numerical simulation and proved that the heterogeneous char oxidation and the homogeneous flame chemistry are also comparable. So I think once we understand this glowing process, we can have more insights about the transition between smoldering and the flaming process. And the last thing I want to mention is when the oxygen supply is extremely large, you can generate a blow-off. Essentially, most of the blow-off process can be quantified by the Dunkel number. But I want to say the blow-off is essentially a quenching process. It's quenched by too much cold airflow. And the blow-off can also happen for the smoldering. So this is an experiment we do on the smoldering incense. So under a very large wind speed, smothering process can also be blow off. Okay, and also blow off has also widely used in the firefighting, especially in the wildland firefighting. So we have to ask a question: what's the boundary between wind-assisted fire spread to the blow off? If you're increasing the wind, you actually helps the fire spread. But if you add too much, eventually you can blow off the flame. So these are the questions we can still explore the boundary. And finally, I just give a very short summary about the review. The first is I personally believe the scientific framework for the fire spread has already been established over the last 50 years. So we know the science very well. And nowadays we can still quantitatively modeling the fire spread process. However, I do not recommend people to trying to do some modeling, trying to match the experiment data. Getting a good agreement is not necessarily useful. Instead, we will need to focus on using the numerical model to understand the process well, to explain many of these near limiting phenomena, such as the fingering, such as the glowing, and all these transition process. These still need to be explored. Another thing is many experiment is done in the small scale lab environment, but most of the fire in the world are large, like facade fire on the building, like the wildland fire in the mountains. So understand these phenomena are still very challenging, okay? And also, in the end, how to apply the science into fire engineering practice is always a challenge topic. So in the end, I like to thank all my supervisors, Professor Foreman Williams, Professor Carlos Fernandez-Payo, Guillermo Rain, Michael Goldner for their really sincere help when I was a student. And I also like to thank all my students and lab mates and assistants, my co-author, Dr. Gao, on this work. I cannot finish this review without their help and support. Thank you for your attention.